All right, everybody. Moving on to the next part of chapter 15, we're going to talk about the fundamental theorem of line integrals. And this is going to result in several really nice, convenient facts about line integrals and conservative vector fields that will honestly make our lives a lot easier. So, without further ado, we're going to start off with an example. All right, so let's say that we have a force field that is acting upon an object that's moving along a path. Our force field is given by the following vector function, vector valued function, oop, plus hat. Okay. And the path that the particle is moving along is given by, we're actually going to look at three different particle movements. In each case, we're going to start at the point 0, 0, and we're going to end at the point 1, 1. Right, so we're looking at vectors in a plane. So for the first part of this example, let's consider C1, where the particle is moving along the line y equals x. When we look at this example, this pathway, um, one approach we can take is, as we've seen before, assigning parametric equations. Since the line is y equals x, we can do x equals t and y equals t. If we want to, though, we could also rewrite this in the entire thing in terms of either just x or just y, and there would be a similar pathway that leads to the same answer. Right, but anyway, if I go with what we've been doing, right, writing parametric equations, x equals t, y equals t, that tells me that r of t, that's the vector valued function that describes the path or the line that we're integrating over, is given by this. Remember to compute a line integral, or actually, before I do that, we're actually figuring out the amount of work done by the force field on the object. So remember, with line integrals, typically we would want to find the magnitude of r prime. But remember, when we're calculating work, we're evaluating this line integral that uses that weird notation where we have a force field dot a differential. All right, so remember in this case, because I need the vector form of the derivative of r, I'm not going to take the magnitude, I'm just going to take r prime. So r prime of t would just be the vector 1, 1, right? Derivative of t with respect to t is 1. So um, the other thing I would need to do is make sure that I rewrite my force field F in terms of t, right? So if x and y are both t, then the I component would be t squared over 2. The j component would be 1/4 t squared. All right, so keeping in mind that we also need to figure out the values of t. If we're going from 0, 0 to 1, 1, that means that t is going to take on values between 0 and 1. So the bounds for my integral will be 0 to 1, right? Force field written in terms of t will be 1/2 t squared, 1/4 t squared, dot, and then r prime of t is 1, 1, so dr would be 1, 1 dt. And now I take my dot product. First times first plus second times second. So we get the integral from 0 to 1 of first times first, that's 1/2 t squared, plus second times second, that will be 1/4 t squared with respect to t. Since these are like terms, we can combine them. So we get 3/4, make that look a little bit more like a 3. integral of t squared dt. So using my power rule, I end up getting t to the third over 3. Since I divide by 3, the result will be just 1/4 t to the third. And we're going to evaluate that from t equals 0 to t equals 1, the result giving us 1/4. So the work done by that force field taking that path is 1/4. So we're going to now look at the same force field, but this time we're going to go along a different path. We'll call this one C2, where our particle is moving along the line x equals y squared. So if we're still going from 0, 0 to 1, 1, just a side note, t would still range between 0 and 1. So we can also write parametric equations for this one fairly easily. Remember, if you have something raised to a power in an equation like this, it's usually a good idea to make whatever's raised to a power the t, right? So if I let y be equal to t, then x is just going to be t squared. Now that I have my parametric equations, I can write my vector valued function r. So we get t squared for the x component, t for the y component, which means that r prime is going to be 2t for the x component, t for the y component. Or no, that's not right. 1 for the y component. All right. So now that we have all of this, keep in mind we do need to rewrite our force field in terms of t again, because we have different parametric equations for this pathway. So with that said, we're taking the integral over C2 of f, the force field dot dr. Remember, dr is just r prime of t dt. We need the vector form because we have the dot product version of the line integral. Right, so no magnitude here. With that said, we know that t is still going to go from 0 to 1. Those are the bounds. If I rewrite f, this time I'm replacing x with t squared and y with t. So my x component for the force field is going to be t cubed over 2. And the y component for my vector field is going to be 1/4 t squared squared, so 1/4 t to the 4. All right, that's rewriting the force field using these new parametric equations. Then we're going to take the dot product of that force field with r prime. So that was 2t 1, and then integrate with respect to t. So taking my dot product, first times first, the 2's are going to divide and I'll be left with just t to the 4 plus, then second times second, I get 1/4 t to the 4. If I combine like terms, I will get 5/4, which I'll bring out to the front, t to the 4. And I can use my power rule to find the antiderivative. Add 1 to the power, that'll be t to the 5, divide by 5, that makes this 1/4. And we evaluate from t equals 0 to t equals 1. I get 1/4 minus 0, which is also 1/4. And your textbook actually goes through a third pathway that also ends up giving us the same value for the amount of work done. So this is kind of interesting because this shows that the work done, or this is an example of, I shouldn't say this shows, but this is an example of the work done in an object being independent of the path along which the work is done. Right, so the physics definition of work, not the real life definition of work, because if I had to go in this big O loop-de-loop pattern, that's way more work. All right, but in the physics sense, right, it doesn't matter if I take the straight line from 0, 0 to 1, 1, or if I go along a curved path from 0, 0 to 1, 1. we still compute the same amount of work. That's to say, it's independent of the path. And this is actually one of the results of our fundamental theorem of line integrals. The important thing to note here is that if we look at our original force field, so done with the example, if we look at our original force field F, which I should do in my folder. There we go. We had xy over 2I plus x squared over 4j. Okay. If I take the derivative with respect to y of my I component, I end up getting x over 2. Okay. If I take the partial derivative with respect to x of my y component, I end up getting 2x over 4, but guess what that simplifies to? Because these mixed partials result in the same thing, remember what that means. That means that F, this force field, is conservative. Because the force field is conservative, the amount of work done on, or the amount of work done by the force field is independent of the path. And this is generally true for conservative force fields, which is why this is something that you see a lot with gravitational fields and electric fields, because they're all conservative. The amount of work done on a particle in either of those fields is independent of the path. Let's delve a little deeper into this idea. So first off, we determined in that last example that the force field F was conservative. Remember, what does it mean for a vector field to be conservative? It means that that vector field is the gradient of some potential function little f. Right. So now on to the actual fundamental theorem after which this section is named. Think back to your fundamental theorem of calculus, way back when you were an eager, bright-eyed Cal 1 student. You learned, write this here, fundamental theorem of calculus. All right, you learned that if you take the integral of a derivative from a to b, that it's equivalent to f evaluated at one endpoint minus f evaluated at another endpoint. Okay, that's your fundamental theorem of calculus. If you take the integral of a derivative, you get the original, and if it's definite, you subtract what you get from plugging in the endpoints. The fundamental theorem of line integrals I don't know if I want to put an I there. Well, can if you want. So the fundamental theorem of line integrals is just an extension of this. In fact, the fundamental theorem of calculus is used in the proof of the fundamental theorem of line integrals, which I'll spare you from. If you really want to see the proof, you can look at it in section 15.3 of your textbook. Yep. So the fundamental theorem of line integrals basically tells me that if I take the integral over some path of a force field dot dr, right? So basically, if I integrate a vector field, I'm essentially integrating, right? I'm essentially integrating a gradient. So if f is conservative, right? F is conservative implies that f is the gradient of something. If I take the integral of a gradient, guess what I'm going to get? The original thing. So if we write this as the integral from a to b of essentially our gradient, oh, whoops, wrong thing. Little f dot dr. Yep. That's essentially going to give us the potential function at point B minus the potential function at point A. So it really is just the fundamental theorem of calculus, except now instead of talking about definite integrals, we're talking about line integrals. Fundamental theorem of line integrals. If you take the integral of a gradient, you get the potential function. Big news. But what's cool about this is that it actually makes doing a lot of these problems where we're calculating work and evaluating those different kinds of line integrals, it actually gives us an option if we know that our vector field is conservative, that typically is going to be a lot quicker than the process, the long drawn out process that I've talked about in the last couple of videos. Let's look at an example. So let's say that we want to evaluate the line integral of some vector field f dot dr over a path C, where C is a piecewise smooth curve, which basically means that the derivatives of R are continuous. All right, that takes us from -1, 4 coordinate to 1, 2. All right, and we're given that the vector field is described by 2xyi plus x squared minus yj. Okay. So here's the thing. One of the big results of this is that it does not, if we can show that this is a conservative vector field, then it does not matter how we get from this point to this point, only that we get from this point to this point. So first, let's look at F and let's double check and make sure that this is a conservative vector field. So this is our first kind of step is F conservative? All right, and in that case, remember we just take the partial with respect to y of the x component. So partial with respect to y of 2xy. And we compare that to the partial with respect to x of the y component. Now, if I look at this, derivative with respect to y will be 2x. Okay. Look at this one, derivative with respect to x will be 2x minus 0. So 2x. Since the partial derivatives are equivalent, we determine that yes, the vector field f is conservative. Because the vector field f is conservative, that tells me that the integral over the path C of f dot dr is going to be equal to my potential function evaluated at the final point, 1, 2, minus my potential function evaluated at the initial point, -1, 4, no matter what path I take. So before we can carry out this calculation, we need to go back and figure out what the potential function is for the vector field f. All right, and if you remember from a couple or last video or a couple videos ago, I don't remember, a couple videos ago, yeah. Right, we can figure out the potential function by integrating the different parts of the vector field f. So if I take the integral of my x component with respect to x, because remember, if this is the gradient, then this was fx, then I get x squared y plus some function of, or plus some function that involves the other variable. If I take the integral of my y component with respect to y, because remember if f is a gradient, then this was fy. Then I get x squared y minus y squared over 2 plus perhaps some function involving the other variable. So now that we've laid this out, we know everything, or we know all the different parts that involve x and that involve y. So I know that my potential function f as a function of xy is going to be x squared y minus y squared over 2 plus a constant c. And here's the thing, when we go through and do this one, kind of like how you always say when you do a definite integral, you don't write the plus c because when you subtract it, it goes to 0 anyway. What's going on? Why is that bird on top of the other? Oh, that's weird. Interesting. Okay, y'all. I'm sorry. I took my meds this morning, I swear. Anyway, the same idea applies here when we subtract our potential function evaluated at one point from that same potential function evaluated at another point, the constants are going to zero out. So this doesn't actually matter because we're evaluating at a point. So now that we've figured out the potential function, we can go back here and box all this off, right? And we can just plug the numbers in. So if I plug in my final point, 1, 2, I get 1 squared times 2 minus 2 squared over 2. From that, I'm going to subtract, and here the parenthesis is important, f of negative 1, 4. All right, so that's going to be negative 1 squared times 4 minus 4 squared over 2. And then doing a little arithmetic, I get 2 minus 2, so that's 0. And then I have 4 minus 8, which is negative 4. Multiplied by the negative, we get 4. So the value of that integral is 4. And now we've seen how we can use the fundamental theorem of line integrals to make it so that we can side skirt all of the parameterization and finding gradients and finding R prime and taking dot products and blah, 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 blah. Yeah. All right, let's look at another example that involves a function of 3 variables, just so we have it. So here we're going to have a vector field F defined by 2xyi plus x squared plus z squared j plus 2yzk. All right. So at this point, oh, we need the C. So our path C is going to begin at the point 1, 1, 0 and end at the point 0, 2, 3. Right. And we want to compute the integral over the path C of f dot dr. So again, we want to make sure that we're looking at a conservative vector field before we try to invoke the fundamental theorem of line integrals. Because remember, this is only going to work, pun intended, if if F is a conservative vector field. Otherwise, remember, there's no point in looking for a potential function because if F is not conservative, then that means that it's not the gradient of anything. So with that said, remember the way that we check for whether a vector field is conservative in three variables involves the curl. So we have to calculate the curl of F. Remember, that's going to be your differential operator del cross the vector field itself, F. And remember, that's going to take a 3 by 3 determinant. So we have ijk. Second row, we have our differential operators, partial with respect to x, partial with respect to y, and partial with respect to z. Then in our third row, we have the components for the vector field f. So I have 2xy, x squared plus z squared, and 2yz. So writing this out, we get our I component for the curl. That's going to be, you take these out, partial with respect to y of 2yz, that's going to be 2z, minus partial with respect to z of x squared plus z squared. X squared will go away, z squared will become 2z. So far, so good. Now for our j component, which we have to subtract, right, we have partial with respect to x of 2yz. There's not an x in that expression, so that would be 0. Minus the partial with respect to z of 2xy. There's not a z in 2xy, so that's also 0. All right, cool. Now we only have one more component. So with respect to k, we get partial with respect to x of x squared plus z squared. That's going to be 2x minus, and then partial with respect to y of 2xy. That's also 2x. So our curl ends up being the 0 vector. Remember, if your curl is the 0 vector, that means that f is conservative. And because we know that we're going to need the potential function to use the fundamental theorem of line integrals, we are going to go ahead and find out what that is. So if I take the integral of 2xy with respect to x, right, I component integrate with respect to x, I get x squared y plus some function involving the variables that are not x. So y and z. When I take the integral of the j component, we're doing integral of x squared plus z squared dy, right? For the first term, I'll get x squared y, which already popped up, plus yz squared, which hasn't popped up. That's going to be part of that guy, plus some other function that perhaps involves the variables that are not y. Right, and since we already took the integral with respect to x, we know that there's not going to be anything involving x and z. There might be something with z though. And then lastly, we have to do the same with our z component. So we're going to take the integral of 2yz with respect to z. So that's going to give me yz squared, right? 2yz squared over 2, the 2's divide, plus perhaps some function that involves the variables that are not z, right? Which we already know is going to be the x squared y. So looking at this, we get all the terms that involve x, y, and z. So I know that my potential function in terms of x, y, and z is going to be x squared y plus yz squared plus a constant c that I don't need to write because remember, we're going to use the fundamental theorem. So the constant is going to subtract out anyway. So with that said, I know that the integral over the path C of f dot dr is going to be my potential function evaluated at the endpoint, which was, whoa, not 0, 23, 0, 2, 3, minus the potential function little f evaluated at 1, 1, 0. So if I evaluate this guy at 0, 2, 3, x is 0, so that first term is 0. For the y part, we get 2 times 3 squared, right? 2 times 9, that's 18. That's the value of f of 0, 2, 3. From that, we're going to subtract what we get from plugging in 1, 1, 0. So here the z is 0. Try saying that 5 times fast. So the second term will zero out, and we'll be left with 1 squared times 1, which is 1. If I subtract 18 minus 1, I get my answer, 17. So it doesn't matter what path, right, what path I take to get from 1, 1, 0 to 0, 2, 3, if f is my force field, I can choose any path I want, and I'll end up getting 17 for my line integral. Yay, fundamental theorem. Okay, all right. Because I want to specifically point out this case, I'm going to do an example that is not in the textbook. So I'm going to make one up here. Actually, you know what? I don't even really need to make an example. Let's just take a look at this one that we looked at before. Okay. So before we had this in a previous video, we had this case where we had a particle that starts here, moves along the line, comes back along the parabola. The point is that we start and stop at the same point, right? We begin where we end. We end where we began. Philosophical. Wow. Okay, so if this were the case, right, so this drawn out thing is my C. Remember, we had a specific notation for something like this. So this is a case where we have functions that are simple and closed. Okay. I think that gets, yeah. All right, simple and closed. So essentially, I'm taking the integral and we're moving along a closed path, and we're moving in the clockwise direction. Right, so remember the integral with the circle in it just means that your path that you're integrating over is closed. You end where you begin. The arrow just tells you what direction you're moving in. All right, if I take the integral of this with whatever force field dot dr, if f is a conservative vector field, okay, f is a conservative vector field. Remember, that means that this integral is essentially just the potential function evaluated at the final point minus the potential function evaluated at the beginning. Well, here's the thing, y'all. If we start and we stop at the same point, these are going to be the same values. And if I subtract anything from itself, I always get 0. Yep. So if you have a case where the fundamental theorem of line integrals applies and the path that you're taking is closed, right? And there's no weird hanky-panky happening with these pathways, then your line integral is zero. Yep. Which is another really, really powerful result of the fundamental theorem of line integrals. Because, I mean, in all honesty, there's a lot of things in the physical world that are on closed paths. So this gives you some pretty applicable insight. All right, and then for fun, we'll do one more example just to kind of keep our minds in this space, and then I will end the video. All right. So for this last example, let's say that we want to start off with this force field. F is equal to y cubed plus 1i plus 3x squared plus 1j, or 3xy squared plus 1j. All right, that's our force field. C is a semicircular path. From the origin 0, 0 to the point 2, 0. So essentially you're moving along a semicircle centered at 1, 0 with a radius of 1. Which if you really wanted to, you could write as x squared, or actually, since it's a semicircle, y equals only the positive square root of 1 minus x squared. Okay. So if you wanted to write the path out as a function involving x and y, you could do it that way. There's not really much point to that though. So let's say that we want to evaluate a line integral for a particle that's traveling along this path, undergoing work done by this force field. That's to say we want to know the integral over the path C of the vector field F dot dr. Okay, we have options because now we know about the fundamental theorem of line integrals. We know how to find conservative vector fields. We know how to find potential functions. We have all the tools that we need to make this potentially, pun intended, as easy as possible. I don't know why people say pun, no pun intended. Intend your puns, cowards. All right. So first thing, because this is a function of two variables, it's pretty quick for me to check and see if f is conservative. So start off by checking my mixed second partials. Remember, you differentiate the x component with respect to y. So d dy of y cubed plus 1. If I do that, I end up getting 3y squared. Then we take the partial derivative with respect to x, of our y component. So that's 3xy squared plus 1. When I take this derivative, I get 3y squared. Because these mixed partials are equivalent, we know that f is conservative. And because f is conservative, we know that the fundamental theorem of line integrals applies. Another thing, if I noticed at this point, so if I've determined f is conservative and I know that my start and end point are the same, I automatically know my answer is 0. No other work would need to be done in that case. But here the start and finish points are not the same, so we do need to do a little more work. So with that said, we need to figure out what the potential function is. So we can do that by integrating the x component with respect to x. Right, I'll get xy cubed plus x plus perhaps a function that involves the variable that's not x. Then I'll take the integral of the y component, 3xy squared, plus 1 with respect to y. So I would get xy cubed, which already popped up in the other one, plus y, plus perhaps some other function that involves the variable that's not y, which we already know is going to be this guy. So if I combine all of the pieces together, I get that my potential function f of xy is xy cubed plus x plus y, and then there's a plus c, but because we're going to use our fundamental theorem, I'm not going to write it. So now that I've done that, I can say that the integral over the path c of f dot dr is equal to the potential function evaluated at my final point minus the potential function evaluated at my initial point. If I plug 2, 0 in, x is 2, y is 0, I get 0 plus 2 plus 0. Okay. If I plug 0 in for both x and y, I get 0. So my answer is 2. And the thing about that one is that you don't necessarily have to use the fundamental theorem of line integrals to do this, right? You're given enough information about the pathway C that you could write parametric equations for x and y. And with that, you could do what we did before, right? So that said, we have talked all about the fundamental theorem of line integrals. So remember, always look and see if the vector field that you're working with is conservative, because if it is, then you have potentially, oh, then you potentially have other options to compute your line integrals, some of which might just consist of looking at the starting and ending point and saying 0. Right? But anyway, that's all for this video. Happy mathing.